Welcome to the first part of our lecture series on superconducting resonators. This series is brought to you by the NYU Nanolab, the Laboratory for Quantum Materials and Devices. We would also like to give special thanks to the NordTech Hub and the Microelectronics Commons for making this lecture series possible. In this presentation, we'll explore how electrical resonance works from a circuit theory perspective, focusing on resonators made from lumped devices, such as resistors, inductors, and capacitors. Before we begin, let's quickly review the difference between lumped and distributed elements. A lumped element is one that is much shorter than the wavelength of the electrical signal it operates on. When we combine lumped elements into a circuit, their overall behavior can be accurately described using circuit theory. In contrast, distributed elements have physical dimensions that are comparable to the signal's wavelength, and their behavior must be described using transmission line theory. In the upcoming sessions, we'll build on the lumped element resonator concepts we covered today and connect them to transmission line resonators. Our main objectives for this session are, first, to understand the basic concept of electrical resonance and the LC oscillator. Second, to describe the two primary lumped element RLC resonators, parallel and series. And third, to derive the module of their input impedance at resonance. Let us now start by defining the concept of electrical resonance. Electrical resonance is a condition that occurs when a circuit is excited by a periodic signal whose frequency matches the circuit's resonant frequency, omega 0. At resonance, the circuit produces a disproportionate response. Whether this response is beneficial depends on the circuit's intended application. For example, resonant circuits, the main topic of this lecture, are circuits that exploit this condition and are used to build devices such as filters, oscillators, frequency meters, and tuned amplifiers. For those who enjoy a bit of history, let us take a brief look at how Heinrich Hertz created the first electrical resonance plots more than 130 years ago. This is a simplified electrical schematic of his experiment, in which he had a spark gap transmitter and a receiver. In case you're wondering, this is what the receiver looked like: a simple wire loop with a micrometer spark gap at its ends. When Hertz pressed the switch SW, a spark jumped across the transmitter gap S, creating a pulse of radio waves. These waves were detected by the receiver and induced a tiny spark across the receiver gap M. Hertz then studied this effect in more detail. He measured the spark length, shown on the y-axis of these plots, while varying the loop length of the receiver, shown on the x-axis. He kept the frequency of the transmitted pulse fixed. What he observed was remarkable. The spark length peaked when the receiver's resonant frequency matched the transmitter's frequency. These plots became the very first published electrical resonance curves. Alright, that's enough history. Let's get to work and start examining the concept of natural frequency through a more practical lens, the lens of circuit theory. Consider this basic parallel LC circuit and designate the voltage across the capacitor as Vc and across the inductor as Vl. The capacitor and inductor share the same voltage, therefore, applying Kirchhoff's voltage law, we obtain the equation shown here. Now, we substitute both Vc and Vl by their corresponding volt-current relationships, and, since the current through both elements is the same, let's replace IC with IL in both terms. Finally, we differentiate with respect to time and divide through by L to obtain this second-order differential equation. This is the equation of a simple harmonic oscillator, which is basically telling us that the current in this circuit swings back and forth in time. Let's take a closer look. The general solution to this equation is given by this sine wave, where A is the amplitude, phi is the phase, and omega 0 is its frequency, which is known as the natural frequency of the circuit, because there's no external active force driving these oscillations. From the simple harmonic oscillator equation, we obtain that this natural frequency is equal to 1 over the square root of LC, which means that this frequency is determined by the L and C values independently of the energy in the capacitor or the inductor. To build more intuition about natural frequency, let's look at how the voltage and current in this circuit change over time. The voltage is represented by the blue sine wave and the current by the red one. Imagine we begin by fully charging the capacitor using an external source, and then we let the circuit evolve on its own. At that instant, the capacitor's voltage is at its maximum, shown at the start of the blue sine wave, while the current is zero since no charge is flowing yet. As time goes on, voltage and current begin to oscillate back and forth. When the current reaches its maximum, the voltage drops to zero, and when the voltage is at its maximum, the current is zero. The frequency of these oscillations is what we call the natural frequency. This is also why the circuit is often called an LC tank. In a perfectly lossless environment, the oscillations would continue forever, storing the energy we initially supplied by continuously exchanging it between the capacitor's electric field and the inductor's magnetic field. A lossless environment is a useful ideal, but real circuits always have some losses. Therefore, we model the loss by adding a resistor, R, producing either a parallel RLC circuit or a series RLC circuit. These two configurations capture the behavior of most resonators and therefore form the basis for our analysis moving forward. In this slide, we can see the electrical schematics for both circuit configurations and their corresponding input impedance module versus normalized frequency plots. The center of the plots corresponds to the resonant frequency. Notice that at resonance, the input impedance module of both circuits is equal to R, but their behavior when we move away from resonance is completely the opposite. Let's explore the equations that explain this behavior. We start with the parallel RLC. The input impedance of the parallel RLC is the parallel sum of the three elements' impedances, as shown on the first equation presented in this slide. The second formula are three equivalent expressions for the input power of this circuit. If we take the expression with the voltage module and replace the input impedance by the expression above, we can express the input power as the sum of three separate terms, as shown on the top right side of the slide. On the other hand, the power dissipated by a resistor, the average energy stored in an inductor, and the average energy stored in a capacitor are given by these three formulas. Note that for these formulas, we are using peak values instead of RMS value. That's why the average energy expressions have a 4 in the denominators. Using these formulas, the circuit power can be rewritten as the sum of the dissipated power by the resistor and the average energy of both inductor and capacitor, as presented in this expression. Then, we can take the formula that relates the input power to the current to express the input impedance in terms of the average energy stored in the inductor and the capacitor, and the power dissipated in the resistor as highlighted in the red rectangle. This form clearly shows that Zn has a real part proportional to the dissipated power and an imaginary part proportional to the net stored energy difference. Let's now use this equation for the input impedance we just derived to analyze the case when an input voltage has a frequency equal to the square root of 1 over LC, which corresponds to the resonant frequency of this circuit. The first thing we notice is that the expression for Wm, the inductor's average energy, becomes the same as that of We, the capacitor's average energy. Therefore, if the frequency of the incoming signal equals the natural frequency of the circuit, the average energy stored in the capacitor and the inductor are equal, which is a characteristic of the resonance condition. In this scenario, the input impedance is purely real, equal to the parallel resistance, which explains the maximum value in our input impedance versus frequency plot. For the sake of time, I won't go through the step-by-step analysis of how we derive the input impedance of the series RLC circuit from the power dissipated in the resistor and the average energy stored in the inductor and capacitor. But feel free to pause the video and take a closer look at the steps shown on this slide. As you may have already noticed, this expression is identical to that of the parallel RLC circuit. If we repeat the test of applying a voltage with a frequency equal to the square root of 1 over LC to this circuit, then we can notice that the expression for We, the average energy stored in the capacitor, becomes equal to Wm, the average energy stored in the inductor. Therefore, under this condition, the average energy stored in the capacitor and the inductor are equal, which lead to a purely real input impedance equal to the resistance R. So far, we've seen that for both series and parallel RLC circuits, the imaginary part of the input impedance, the reactance, comes entirely from the difference between the average energy stored in the inductor and the capacitor. At resonance, this imaginary part cancels out, leaving the input impedance purely real and equal to R. In our next session, we'll explore how the magnitude of the input impedance changes as we vary the frequency, and why its behavior away from resonance differs between the two circuit configurations. Let's review what we have learned so far. Electrical resonance involves an electrical circuit and a periodic electromagnetic stimulus. If the stimulus frequency matches the circuit's resonant frequency, the circuit is said to be at resonance. At resonance, the system's response becomes disproportionately large or small compared to its response at other frequencies. An LC pair forms a natural oscillator with omega 0 equals to I over the square root of LC. Lastly, adding a resistor to the LC tank produces series or parallel RLC circuits. At resonance, both input impedances are equal to R, but their frequency responses as you move away from resonance are the opposite. Thanks for watching, and see you in the next session.